This video is available in 21 languages. यह वीडियो 21 भाषाओं में उपलब्ध है. To change the audio.
In May 1999, a skier became trapped beneath an 8-inch sheet of ice in a freezing Norwegian stream. By the time rescue teams extracted her, she had been submerged without a pulse for over 80 minutes. Paramedics recorded a core body temperature of 13.7 degrees Celsius. Her heart was in absolute cardiac arrest. Clinically, she met every diagnostic criterion for somatic death. Yet she survived, recovered, and is a practicing physician today. Her survival suggests that the standard timeline for brain death is more flexible than previously understood. It highlights a critical clinical question: how cold exposure specifically alters the brain's metabolic clock to prevent necrosis. To understand the deviation in the Norwegian case, we have to look at why a standard cardiac arrest is so rapidly fatal. At a normal body temperature of 37 degrees Celsius, the human brain consumes 20% of the body's resting metabolic energy. Almost all that energy powers sodium-potassium pumps, maintaining the electrical charge across neural membranes. When blood flow stops, this system collapses. Without oxygen to produce ATP, energy reserves hit zero in exactly 3 minutes. The pumps fail, and the membrane rapidly depolarizes. This depolarization triggers a massive influx of calcium ions into the cell. The excess calcium activates destructive enzymes, initiating apoptosis, tearing the cellular structure apart from the inside out. At standard body temperature, oxygen deprivation guarantees irreversible internal cellular necrosis in a matter of minutes. We must examine how extreme cold physically arrests this exact molecular mechanism. Thermodynamics and cellular biology provide the framework for this phenomenon, specifically through a metric known as the Q10 temperature coefficient, which measures how chemical reaction rates scale with temperature. This formula calculates the Q10 coefficient. For human brain tissue, that coefficient sits roughly between 2 and 3. This translates to physiology. For every 1 degree Celsius drop in core body temperature, the cerebral metabolic rate for oxygen drops by roughly 6 to 7%. When core body temperature falls to 20 degrees Celsius, cerebral oxygen consumption drops below 25% of its normal baseline. At 13.7 degrees Celsius, the temperature recorded upon rescue, the brain's oxygen demand sits below 9%. This severe suppression of metabolism radically changes how the cell utilizes its remaining resources. Under profound hypothermia, the tissue's demand for oxygen drops significantly faster than the actual oxygen reserves are depleted from the stagnant blood. This widening gap creates a physiological buffer. It maintains just enough baseline ATP to keep the sodium-potassium pumps running, preventing the lethal cascade of glutamate excitotoxicity and membrane lysis. This mathematical decoupling effectively places the brain's cells into a state of suspended animation. By freezing the metabolic rate, extreme cold removes time as the primary variable for death. However, relying on hypothermia to survive cardiac arrest introduces a major physiological paradox regarding how blood delivers oxygen. This chart maps the Oxygen-Hemoglobin dissociation curve. As blood cools, we see a distinct left shift in the plotting. Chemically, this shift means that cold hemoglobin binds to oxygen much more tightly than warm hemoglobin. Consequently, when this cold blood reaches the capillary beds, the hemoglobin refuses to release its payload. The oxygen remains trapped in the bloodstream, starving the brain tissues even when circulating oxygen is present. This creates a fatal timing problem. If a patient's heart stops pumping before their core temperature has dropped significantly, they suffer normothermic ischemia. The brain dies in 3 minutes, regardless of whether the body cools down afterward. For the cells to survive this failure of oxygen unloading, the brain must be pre-cooled to a state of extremely low metabolic demand while the heart is still beating. Neurological survival is physically impossible unless rapid core cooling precedes circulatory collapse. The patient in Norway survived because the freezing water stripped her body heat away just before her heart gave out, setting up the immense hazard of bringing her back. Reversing this profound metabolic suspension is one of the most incredibly hazardous procedures in all of critical care. Applying standard external warming methods to a severe hypothermic arrest, such as forced air blankets or warm saline infusions, almost guarantees mortality. External warming triggers a phenomenon known as rewarming shock. As the peripheral tissues in the limbs warm up and dilate, Stagnant, cold, highly acidotic, and potassium-rich blood is flushed directly back into the core. When this toxic rush of blood hits the myocardium, the immediate mechanical consequence is refractory ventricular fibrillation, a chaotic, uncorrectable heart rhythm. To bypass this systemic failure, clinicians must rely on advanced clinical engineering, extracorporeal membrane oxygenation, or ECMO. The ECMO circuit serves two immediate functions. It acts as an artificial lung to continuously oxygenate venous blood, and it mechanically filters out the severe metabolic acidosis built up during the flatline. Crucially, the console also functions as an internal heat exchanger. It pulls blood out, warms it, and pumps it back in, rewiring the body's temperature safely from the inside out. This process is deliberately painstaking. The machine is kept under a strict thermal governor, restricting the rewarming rate to an agonizingly slow 1 to 2 degrees per hour. This strict pace neutralizes a severe molecular threat. If oxygen is suddenly reintroduced to ischemic tissues at normal temperatures, it generates massive waves of free radicals that destroy the blood-brain barrier. ECMO functions as a precision biological governor. It titrates electrolytes and temperature to protect cellular structures until the body's own metabolic autoregulation can resume. Boundary condition anomalies, like the 1999 Norwegian case, forced the global medical establishment to rewrite fundamental triage protocols and the clinical definition of death itself. Today, the modern clinical mandate is absolute. No severe hypothermic cardiac arrest patient can legally or clinically be declared dead at the scene. Strict guidelines dictate that extracorporeal pore rewarming must be attempted in a hospital setting before any declaration of somatic death is permitted. Instead of a ticking clock, modern intensivists look to the definitive biological point of no return: serum potassium concentration. A serum potassium level exceeding 12 millimoles per liter indicates irreversible systemic cellular breakdown. This serves as the ultimate physiological limit, regardless of the patient's core temperature. Molecular biomarkers, rather than the mechanical absence of a heartbeat, provide the only definitive proof of systemic cellular destruction. The 1999 Norwegian Anomaly provided the physiological evidence required to establish new resuscitation criteria for hypothermic arrest. The absolute boundaries of human brain survival are not, and have never been, fixed by a stopwatch. Neurological survival is exclusively dictated by the precise manipulation of the cellular metabolic rate, paired with flawless mechanical preservation. In our next clinical investigation, we examine a psychiatric patient whose reality fracture was triggered by antibodies attacking her brain's receptors, a biological cause often mistaken for mental illness. Tap the case file on screen to watch now, and subscribe to Biomatrix Education to continue exploring the uncompromising biophysics of extreme medical science.